All right, so welcome to week 3. And this week we are playing with scatter plots. And linear models. And that is sections 2.5 and 2.6. And so we're going to scratch the surface on both of those today. And then we're going to do more with visual displays of data on the next class. And that one is section 2.7. I think I have the numbers right there. And again, I'm not at my best today, so if I make a mistake, somebody please speak or chat to me. So scatter plots. So a scatter plot is a graph of two quantitative variables. So think back to your algebra classes. That's where we had to decide on some variable is going to be X and this other variable is going to be Y. And then we just plot the points and see what happens. Sometimes points line up and sometimes they don't. So let's look at a few examples from StatKey. So StatKey is a website that accompanies our book. And I'm going to go to their base homepage here. I'm going to put this in the chat if anybody wants to go there and play with me, if you don't already have it bookmarked. If I can find the chat. Sorry, again, I'm at home on a different computer than usual. Chat. All right, so in the chat is the link if you want to check it out. And then so far we've played with one quantitative variable. The week before was a categorical variable and a little bit with quantitative and categorical. I'll come back to that. We're going to look at two quantitative variables this week. So mainly in StatKey, this is the only page we need, this last one in descriptive statistics and graphs. And StatKey has a bunch of data here. So they just give you a brief mention of what the data is. It comes from the Florida Lakes data set, which we can get from my Google Drive or from the StatKey homepage. So a reminder about that. If we go to statistics, unlocking the power of data, and then data sets. This is our third edition here. Here are all the data sets. So if you wanted to go grab the Florida Lakes data, you can. It's somewhere in here, A, B, C, D, E, F, Florida Lakes right there. So you can get the Excel version or the CSV version. So let's say I want to get that right now. Zoom screen away, save. And then I could open it up in Google Drive if I wanted to. So let's go back. Where should we put it? I'll just throw it into the general drive. So either the Excel version or the CSV is fine. And it's in order. B, C, D, E, F. It's here somewhere. Probably right in front of me and I don't see it. Where is it? Okay, search for it. Florida Lakes. Huh, Google, where's the one I just put in here? Okay, so I'm having technical difficulties there. Should have just appeared. Alternatively, I have a spreadsheet program on my computer. And if I click it in my Chrome, it should just pop up. Sure. So here's all the original data. Now, although I have all of the data here, I still don't have details about the data. So if you want to know what each variable means, then you have to go to the back of the book and look that up. So in the back of the book, it tells you what each variable is. I think I'm digressing a little bit. And on the wrong page. Okay, so anyway, I had to look these up. So pH, each point here is a different lake. And then the pH was, they took some water samples and they measured the pH. So the pH measures how acidic or basic a particular liquid is. These have pHs. Water, I think, is normally around 7, which is kind of neutral. Some of these are a little basic and some of them are a little bit acidic, is my recollection about PAC. Average mercury, that's a measurement on fish they caught. So they caught a bunch of largemouth bass in these, and then somebody biopsied the bass, took a sample of meat from the fish. Actually, they killed the fish and autopsied it. And they measured how much mercury was in their flesh, their meat. And that was measured in micrograms per gram of mass of the fish. So what this shows is that there's a wide variety of pHs, low pH, high pH, and then high mercury in fish and low mercury in fish. And they're wondering, if the pH is higher, do the fish have less mercury? pH is lower. I kind of see a downhill trend, although it's pretty cloudy. We can push this button here and they'll draw a line through it with a mathematical measurement of the trend of the data. This kind of trend in data is called association. So, important idea for today, association. Is there a trend in the scatter plot? Question mark. Now, typically with the scatter plots, we are looking for a linear trend. Now, there are many kinds of association, but we are concerned about linear. So our concern, do they kind of line up? And those points kind of line up, but they're pretty cloudy. They have a bunch of other data sets here. So let's look at another one. The cricket chirp ones is pretty cute. So some researchers, many researchers have looked at this. And here they're showing chirps. And the chirps here, if you look up the data in the back of the book, this is also in section 2.5, the chirps means chirps per minute. So a particular cricket was heard chirping 67.5 times per minute on average. No, I got that backwards. 123, chirps is the X value here, 123 chirps per minute. And the temperature at the time it made those 123 chirps per minute was about 67.5 degrees Fahrenheit. So each point is a different one. So this one, cricket was heard chirping 150 times a minute, temperature was 72. These guys line up pretty well. Now, there's not a lot of points, so that's also a concern. This is a very small data set, but there are other bigger data sets out there that show pretty much a similar thing, that as the temperature increases, the number of chirps increases. Another idea related to this is the variable type. So back from your previous math, you might remember looking at independent variables. That was usually X, and a dependent variable. That would be Y. X is our horizontal variable, Y is our vertical variable. In statistics, we have different names than independent and dependent, but those ideas still fit. We have an explanatory variable, and we have a response variable. So for example, response. Does the change in temperature explain the response of the crickets where they start chirping more? Right, that kind of makes sense that that might happen. It warms up, cricket gets a little more mobile, starts chirping more, woo. So with that in mind, the cricket chirping doesn't change the temperature. So I'm going to switch the variables here. I think it's the temperature that switches, that causes the crickets to chirp more or less. If it's cold, they slow down, they don't chirp as much, not as joyful maybe. If crickets feel joy. Now the other way is kind of interesting though. Because if I'm outside and I count the number of chirps, I can then estimate the temperature, which is kind of neat. So I could make the relationship go the other way, but in terms of cause and effect, it makes more sense this way. right? That the temperature is the cause of the crickets chirping per minute more. All right, let's look at some other examples. This one I think is an interesting one, sort of, and turn off the lines for now. So on this one here, we have the bill of a patron at a restaurant. So they went out to dinner, and like this one right here, the dinner was $35.68. And the 5 is a $5 tip. And so the tip is the Y value. Remember when we plot points, it's the X value first, that's the horizontal variable, Y value second. So here a bill of $31.94 led to a tip of $8.06. So that person was trying to make their bill a whole number of dollars, which I used to do, but it's kind of annoying for the restaurant or the person that's getting the tip. Anyway, another story. So I do see an uphill trend to this data. So is the bill associated with the tip or the tip associated with the bill? The answer looking at this graph is, yeah, it seems as the bill increases, the tip increases. So we would say there's a positive association here. Some other big ideas. So again, we have an explanatory variable or response variable. Oops, that was supposed to be a straight line. Let's try that again. Wish me luck. Oh, a little better. So ideas about association. Association can be positive. And a positive association means an uphill graph. And let's see, do I have my lefts and rights straight today? I do, yeah. So as we move from left to right, it goes uphill. So that's what I'm showing here. In terms of like equations of lines, that's like a positive slope. And then association could be negative, which isn't a bad thing. Negative, there we go. Which means it's going downhill from left to right. And that associates with a negative slope of a line. Hang on, I'm checking out the slide, that chat. Okay, so again, if you do have questions on the homework, be sure to get in touch with me about it. I see some questions there that I can't answer at the moment, but we're glad to help you individually. And not slop, but slope. So association, again, is looking at a trend. We are looking at linear trends, but not all trends are linear. So I just want to show some other examples. Let's take a look at countries, rural versus area. So here, the area is the size of the country, probably square miles. That's not too important. And then what percent of the country is rural? And notice there's not, this is just a small sample. It's not all countries. There are how many? 10 countries in this particular sample. We have all the countries. We could plot them if we want. But what I see here is most of the countries are up here, and there's several trends going on here. And then these two down here are kind of unusual compared to the rest. So when we're playing around with scatter plots and lines, a few things that we need to consider in general. So scatter plots and lines, considerations. One, do you see an association in the scatter plot? Do you see a trend? So that's the first thing to consider. Second thing to consider, does it seem to be linear? And the third thing to consider, do there appear to be outliers? Question mark, question mark. So if there does seem to be a trend, so if I can answer yes to that question, and if it does seem to be linear, I can answer yes to that question. And do there appear to be outliers? If I can say, nah, there's not really any outliers, then I'm going to look for a linear model. By a linear model, I mean an equation like y equals mx plus b. And to find a linear model means to find m, calculate a slope, and find the y-intercept. And y-intercept, we can consider a starting point or initial value. So when I'm looking at this data right here about countries, percent rural versus area, I don't really see a strong linear trend here, an association, and I definitely have some outliers. So as far as finding a line, I really don't think it's worth it. However, if I go back to like the Florida lakes, although it's kind of cloudy, there does seem to be a downhill trend to these points. So maybe it's worth finding that line there. And StatKey very nicely says, hey, well, if you want the line, the slope is negative 0.152 and the y-intercept is 1.531. And here's the graph of that line. Okay, cool. And then we can then do something with that. Like we could go to a lake and measure the pH and say, hey, this pH is pretty high. The bass probably have very low mercury levels, so it's probably safe to fish here and eat the bass because you don't want to eat mercury. Not good. With the cricket chirps, there's a pretty good pattern here. I see an association between the variables. It looks linear, and I don't see any outliers. There's no points way out in the fringes compared to the rest of them. So yeah, okay, let's find an equation for a line for those points. And again, notice these points aren't perfectly lining up. They deviate a bit from the line, and that's okay. In reality, no points line up perfectly unless it's kind of fabricated. With the restaurant tip, turn off that line for a second, I see an uphill trend, and I was kind of taught social etiquette that when you go to a restaurant, you should give a tip. And usually the tip depends on a couple of things. One, how much did you spend? And two, how good was your service, right? So if I went to a restaurant and I spent, say, $50 and the service was amazing, they were always checking on me and making sure I had what I needed, then, I might give them a pretty good tip, 15-20%. But if I went to a restaurant and the service sucked, I'm always looking for the waiter, they brought me the wrong food, it was cold, I might not give a tip at all. But it wasn't the waiter's fault in most parts, so maybe I give a tiny little tip. So for the most part, though, assuming the service was good, the higher the bill, the higher the tip for most people. So is it worth finding a linear model? Sure. And then StatKey tells us here's the slope, here's the y-intercept. All right, let's see. So big ideas from 2.5, one more big idea. So we look at a situation, we say, okay, there seems to be a trend, it seems to be linear, there's no real strong outliers. So then we proceed with finding a line. When we do find a line, this type of line that we find, this linear model that we're going for, is called a linear regression equation. And it's of the form y equals mx plus b. And when we do the calculation, we're calculating based on the data three things. M, what's the slope? B, what's the y-intercept or initial value? And the third one is R, which is called the correlation coefficient. And what the correlation coefficient does is it measures the association. So it's a measurement of linear association.
Where did the R come from?
We're going to get that either from Stack or a spreadsheet.
Okay.
So what I'm pointing out now is there's three things that we calculate when we run a linear model. One, we want the slope. Two, we want the y-intercept. And three, we want to know what R is. And so if I look back at stat key, I'll show you how to do this in the spreadsheet in the next part here. It gives me the correlation, that's my R. It gives me the slope and it gives me the y-intercept. Now, a little more detail about that measurement of the association. And again, association just means, does there seem to be a relationship when you graph these X values with the Y values? Do they seem to be related in a line, right? That's the thing we're trying to estimate here. So number line, considerations for the correlation coefficient. Oops. So R is going to live somewhere between -1 and 1. And right in the middle is 0. If R is a positive number, right, these are positive numbers here, that's called positive correlation. And all it tells us is really there's a positive slope, right? The graph goes uphill, not downhill. If we find that R is a negative number, it's not a bad thing. That just means there's a negative slope when we look at the graph. So when we look at the graph, we should see a downhill trend. Now, the points could be tightly packed or really scattered and cloudy. And so as far as that goes, if they're tightly packed, that's called strong correlation. So that means you'll get a number close to 1 or close to -1. If R is closer to 0, however, let's choose red for that. This is a weak correlation. And if the correlation is too weak, then there's no point in finding a line. It's not useful. But if the correlation is strong, then that means the line could be useful in predicting other situations that we haven't measured. So correlation, when we talk about it, is either strong or weak. The points are kind of tightly packed around the line, or they're kind of cloudy around the line. And then it's either going uphill or downhill, positive slope or negative slope. So those are the things R tells us. So let's look at some of the values of R from stat key on this data. So here we can see the correlation. Let's blow that up a little bit. There we go. Is about 0.9. It's pretty close to 1, which means the points have a strong connection to a line, this line in particular. There are a couple of points that are a little bit outside, but I'm not too worried about them. They don't seem to be too far. Can you measure how far a point is from a line? The answer is yes. We'll talk a little about that next class. And R is also positive here, which means I see an uphill trend to the data. If I look at, say, the Florida lakes here, the computer sees a downhill trend, and I see it too. And I could be biased because that line's in there. But Yeah, I see a downhill trend there. And this is the line that is calculated to mimic that downhill trend. Notice the value of the correlation coefficient is negative, which indicates, hey, this seems to have a downhill slope. And it's around 0.57, negative 0.57. So it's, you know, it's not too close to zero. It's slightly closer to -1. So this has, it's not really strong and it's not really weak. It's just kind of mediocre in the middle.
So at what point is that more valid or
The whole strong or weak thing?
yeah, I mean,
Yeah. So I
is
can't
it over
say
anything
that.
over 0.5? Or
So as a like a general rule, I would say if it's under 0.5, it's too weak. If it's over 0.5, it's strong enough. But it turns out there isn't a definite number. It requires more study. And usually in a second course in statistics, you would get into how to determine if R is strong enough. But we're not going to get to that. That would take another couple of weeks of play to get to. It is in our book later. I can't remember what chapter it's covered in, but we don't get that far. That's covered in chapter 9, which we don't get to. So this is just an intro, just kind of, yeah, around 0.5-ish or negative 0.5. So I think for us, it's good enough to say, let me get my highlighter here, that if our value of R is in here, it's definitely weak. So maybe like for sure, negative 0.4 to 0.4, we'd say, nah, we don't like it. We're not going to bother with a line. But if it's outside of that, let's go for it. And determining that in a more definite way is again, a wee bit more complicated. It requires 2 or 3 weeks worth of study about statistics as to how we determine how good R is. All right, so I'm going to pause here for a moment, take a breath, get a drink.